This is Big Data for AI and Machine Learning in the Cloud, and I am Michelle Solicito. I am Michelle Solicito, and I've worked in software for 35 plus years, mainly in consultancy. The last 8 to 10 years, I've been working in AWS, Google Cloud, and Azure. I'm certified in all three clouds. That includes AWS Solution Architect Professional and many other AWS certifications, many Microsoft certifications, and Google Cloud Professional Architect certification. I'm certified in around 100 technologies, from programming languages to security to infrastructure.
So what is AI? This document is well known in the AI community, and it gives you a picture of how complex the AI area is. And it starts off with parts of infrastructure, analytics and data. Then this is the more mainstream machine learning and artificial intelligence you might have heard about. Things like Databricks up the top, data science notebooks here. Further down, you've got some of these models that you'll have heard of. Let me zoom in on some of this. So, for example, OpenAI, ChatGPT, some of the Google models like Bard, the DeepMind stuff. You might have heard of quite a lot of these, Meta AI, and NVIDIA becoming a big part of this too. There's frameworks around AI, like PyTorch is a quite famous one, Spark is very famous, and so on. That, AI does not take place in a vacuum. It's part of this huge infrastructure, or huge meta structure almost of parts to machine learning and artificial intelligence. So there are lots of components. The most important thing to know, though, is that data is really key to artificial intelligence, and we'll be going through that later. This diagram is a very good diagram to look in and zoom in on all the key components. I'm not going to do it all right now, but I've put the link in the video and in the PowerPoint, so you can go to that link and see more detail of what is in here. But I'll just do a quick pass around so that you can see some of the stuff that's in here. A lot of this stuff down here we'll be talking about later: databases, data access, data flow, OLAP, which is really data warehousing pretty much, data operations and messaging and streaming. We'll be talking about all of this. So there's some key areas, and then up here, more of the data governance and cataloging, because data is much more useful in AI if it's well catalogued and categorized, if you like. So that's important. Just have a look around and see all these components that make up the whole landscape of machine learning, artificial intelligence, and data, and how interconnected they all are.
So there are lots of types of AI. AI includes machine learning, deep learning, neural networks. The main classifications most people use are these four here. So narrow and weak AI focuses on one particular task but can perform it very well, but cannot do anything outside of that area. An example of that is things like Alexa Echo devices. They can only do something they have a skill loaded for. There's a program to respond to particular commands. And you can add skills, but that's all an Echo can do. Generative AI learns to generate from new content. So it learns patterns within existing data and then uses that knowledge to create new content. So the new content can include things like text or photos or videos, 3D models, music, speech, and so on. Some examples of generative AI tools include ChatGPT from OpenAI, which is the one you've probably heard most about, Lambda from Google, there's Bard as well, there's Google Assistant, and so on. Strong AI, this is what we're all aiming towards, has the ability to perform any task that a human can perform in theory. Doesn't exist right now. Super AI is theoretical, um, can think for itself and can experience emotions and so on, and will pass the Turing test. The Turing test basically is a way of asking a human and a machine the same questions and not being able to tell which one is human and which one's a machine. We're still a way off that yet. So where do we see AI? We can see it in natural language generation. So that's when we convert data into natural language so that people can understand that in English or in French or in German. There are smart devices that can interact with users like the Alexa Echo and the Google Home and so on. There are virtual agents and bots that we've talked about already, things like Siri, Google Assistant, Alexa, and so on. There's speech recognition, like Alexa has Lex speech recognition built in, which converts human speech into computer commands. There's augmented reality, things like VR headsets like Quest and so on. They create a different version of reality to be experienced in a different way. Machine learning is whereby machines can learn by themselves without having to be programmed. They learn from patterns and from documents and so on. Robotics, things like a Roomba that you have that vacuums your home and that kind of thing. Also things like warehouse management, picking in distribution centers and so on. You can have robots that go around the distribution center and find the goods and so on. Robotics are being used more and more in Europe, especially where you can walk up to a train station or an airport and so on, and there will be a little robot that comes up to you and asks you if it can be of help, and you can give it commands and say, I want to know how to get to platform 10, and it will give you directions and that kind of thing. Decision management, things like Informatica and Pega and so on, help make valid decisions based on a huge amount of data. Typically, this is going to involve a data pipeline, refining data, and then putting that data into a data warehouse, and using that data for decision management. Deep learning, this is where you have neural networks that mimic the human brain in processing data, and they learn new pathways just like your brain has new neural pathways through it, very similar to the way the human brain works. Image recognition is all about video or image recognition to help in lots of ways, for example, in visually impaired users to be able to see an image and be able to describe it to that person. It's very useful with videos, for example, in YouTube for finding out which YouTube videos have particular content in them from looking inside the video and seeing the content of that video and the text within that video and the speech within that video and converting that into tags that you can search on. Where do we see ML, machine learning? You can see it in image recognition, speech recognition, virtual personal assistants, customer service reps, which are basically automated customer service that allows you to choose from different options and so on. Social media algorithms, fraud detection, streaming recommendations, traffic predictions, self-driving cars, IVR, which is a virtual way of moving through a call system, a call support system typically, where you're told which options are valid in this particular scenario, and you choose one and it moves you to a customer support representative or to some information that you're looking for and so on. How does AI work? So AI works through either keywords and language, for example, through NLP, natural language processing, now called large language models because they're bigger. Semantics, which is all about looking at how language is expressed and what it means, what's the meaning behind that language. So Apache Lucene is a big tool in that area for semantic search. So rather than just look for the keywords that you put into Google search, for example, Lucene allows the similar words or words that mean similar things to be searched for as well. So Google search is based on Lucene. Speech recognition. So this is pattern based, looking at the patterns when you speak and how they correspond to words and letters. Lex in Alexa and AI speech in Azure do that speech recognition. Speech generation, so this is where text in a database is converted into actual words and speech. Things like Polly in AWS do that, AI speech in Azure, and so on. This is getting very complex nowadays. Used to be just word for word. Now it's, whole phrases and taking into account context and semantics and so on as well. Video recognition and detection. There's things like Kismet that can recognize emotions in facial recognition applications. Recognition in AWS does the same kind of thing. They can recognize the spacing in your face and the space between your ears and your nose and work out if you're the same person, that kind of thing. But they can also recognize emotions now, so they can see if you're happy or if you're sad. And interpret that for the person at the other end who might need to know, for example, in a sales situation. Salesforce does this. It might be useful to the salesperson to know that this person is not happy with this proposal that you're talking about. That their facial signs are showing that there's distaste or they're angry or something. So you need to change your pitch and your sales talk. Deep Face can also recognize people's faces. This was created by Facebook. They used it to recognize people in images and videos and tag people in those images and videos. They had to shut that down due to societal concerns. And that's because, for example, people who were African American were getting tagged badly, or they were getting recognized less often and that kind of thing, and so on. So people didn't like it, so they put that on hold until it gets better. There are template-based AI, for example, resume makers like resumaker.ai. So if you want to create your resume, you basically give your old resume to them and they put it into a pretty template with a nice layout, makes it look really good. ChatGPT does a lot of its work through templates. So for example, if you go to ChatGPT and you ask it for a Python application, most of that is just templated code, and the different values that go into it depend on the particular scenario that you're asking for, but the template generator is what's creating your code. I've written a number of code generators, so I know how they work, and it's very complex often, but it's basically just a template with parameters passed in. Rules. Humans teach an AI piece of software how they make decisions, so which rules they use, and those rules are used by the software to make decisions, and it can often feed back into itself and say, we use this rule and we got this result, and how we wanted the result X, but we got the result Y, so let's feed it back in and get Y, and that kind of thing. So for Google AI, for Claims Acceleration Suite for healthcare, that's how that works. So claims come in, decisions are based on particular rules that humans have created, but sometimes the result is not what they'd expect, so they create another rule that counters that particular issue, or remediates that particular problem. So models, a lot of people have heard a lot about AI models lately. So this is where you particularly use existing or past data, huge amounts of it usually, to make predictions or to create decisions or to produce outputs that you're expecting, and again to send that data back in when it doesn't quite match what you expect, to train the model, keep training the model. Google Cloud has a model garden, which is lots of models that already exist that have been trained to a certain extent, but you might want to use them for different purposes, so you can use those as a basis and then build on top of those. They've got Vertex AI and all kinds of other tools in that area. This is just a summary of the tools in the 3 main clouds that you can use for the different areas of ML and AI. So machine learning, typically in AWS, you're going to use SageMaker. Azure, you're going to use something called Azure Machine Learning. And in Google Cloud, you're going to use Vertex AI, pretty much. Notebooks, so Jupyter notebooks are typically the ones that people use nowadays, normally sit on top of some kind of Spark application or platform, and the notebooks are used to generate data, generate outcomes from data, and so on. So Jupyter notebooks are used a lot by data scientists and so on. There's all kinds of AMIs and machines that you can use. I'm sure you've heard of NVIDIA machines that have been used for a lot of this AI and ML. A lot of these things are built on top of that. But this is just a kind of a list across the clouds. So for example, in AWS you use Polly for text to speech, cognitive searches for services for text to speech in Azure, and then GCP has something called speech to text, but they're all pretty much the same thing. Sorry, not speech to text, text to speech. So there's a few other things here, like there's the Translate AI, so those translate from one language to another, from one human language to another, so like English to Spanish or that kind of thing, French to English. There's Translation API in GCP, and there's Translate in AWS. For video intelligence, we talked about that facial recognition software in AWS called Rekognition. There are similar applications in Azure and GCP, as you can see here. Lex in AWS, that all these different options available in the different clouds, basically. These are the AI options in the cloud. So in AWS, you're pretty much going to use Amazon Bedrock. In Google Cloud, you're going to use Vertex AI. In Azure, you're going to use OpenAI. The foundational models, Microsoft has a very close relationship with ChatGPT, GPT. So that's typically what's going to be used there. Foundational models in AWS haven't really been ascertained as yet. There's model catalogs, so SageMaker has a choice of models that you might want to use. It's a bit like the garden that you get in Google Cloud, and the ML foundation models that you get in Azure. The vector database, you can use the RDS PG vector, or the Cloud SQL PG vector in Google Cloud, and the Azure Cosmos DB Azure Cache in Azure. So these are just some of the things that you might use. Code completion, this is one that a lot of developers love. Amazon Code Whisperer basically helps you complete your code in Visual Studio or in the Amazon Code interfaces. Duet AI is the same thing for Google Cloud, and the GitHub Copilot is for Azure. All three pretty much will help you write your code, very similar to the JetBrains tools that you've probably used before. They help you write code, they help you write snippets, they help you format code, they give you suggestions which libraries you should import and that kind of thing. Very useful for programmers.
So you may have heard the terminology LLM, and you may have heard resource augmented generation, or RAG. So what do they mean? So an LLM is a large language model. A lot of people have heard of the OpenAI, ChatGPT models and so on. So these are really neural networks under the hood. Neural networks pretty much work as the human brain works, creating connections between things based on patterns detected in the input data, and they can self-learn. So if you keep putting the data back through, they can continually learn and improve their algorithm almost, and their network, their connections, so that they get better and better at producing the kind of output that is required. So they're pretty much pattern recognition is a big part of that, but they're kind of like an engine that's like a self-improving system. LLMs are particularly focused on the way language works and the way language is connected and sentences are connected and so on. And they can generate more and more complex outputs on that basis. And so things like the ChatGPT model has been trained based on all of the content on the internet, pretty much. So it's really, really powerful because every time that system feeds back on itself with a new, web page or website, it learns more and more about the way humans make sentences, how humans explain things, and so on. And some of the byproducts of that have even been that now it can generate code because it looks at the patterns and almost like templates out there of how code should be written, and it uses those to generate more code, kind of thing. So they're very powerful when they've got a lot of data, but they're very data hungry. They need a lot of data to be useful, to be good. And because the whole of the internet has been used to feed through some of these models, they're very, very powerful, and they can make very good predictions, very good outputs of what the person who's asking the question wants. When someone writes a prompt and says they want something, these engines can analyze that prompt, work out what the person wanted, and produce output that is almost exactly what they wanted based on the whole internet. It's kind of like a search engine on steroids. So what is RAG? So RAG is resource augmented generation, and it enhances these models, and it helps with the accuracy and the reliability of these models. So basically what it does is it kind of checks and self-checks itself and feeds back into itself to make these models better and better and better. And context is added so that, for example, if I ask for a program in Python, it's not just going to create a program, it's going to create a Python version of that program. So it's going to look at the language and how other people have written Python programs. Okay, so that's the context. When you type in, I want a program for summing two numbers in Python, it's going to look at lots of examples of Python programs on the internet, and maybe a lot of examples of programs that actually add two numbers and generate something that is modeled based on all of those inputs. And so RAG just encourages that to be more accurate and reliable and feed back to itself and work out whether the output is close to what was expected or not, and that kind of thing. So it's used with large language models to guide and modify the results based on all the sources that it can find, try to work out how accurate that is and how reliable that is.
Companies that are deeply involved in AI and ML, you've probably heard of ChatGPT from OpenAI. The Microsoft relationship is interesting right now. As you probably know, the guy in charge of ChatGPT got kind of fired for a couple of days, and he went to Microsoft and then came back. But now OpenAI is very, very in bed with Microsoft. So watch that relationship as it develops. Viz.ai are very strong in the healthcare sector for EKGs and X-rays and CT scans and MRIs and so on. Obviously, Microsoft is very big in AI with their NVIDIA Alliance for their chips, Azure Machine Learning as a Service, and they have tools for everything. AWS, obviously, we talked about Poly and Lex and recognition, and Amazon Machine Learning. All three of the clouds are really pushing AI and ML. Databricks you can use on all three clouds. It's basically an AI and ML platform for data. It's been out there for some time. It's pretty mature now. It provides what we call a lakehouse environment with Delta lakes and so on. We'll talk about that later on in the slides. Google Cloud has Google AI, Vertex AI, AutoML, speech to text, text to speech, and others. I talked about the new generation of chips. They've all got that now. So all three clouds now use the NVIDIA chips. Google Cloud build AI and ML into all their social media, their weather apps, their GPS apps, disaster response, so many areas. They have DeepMind neural networks, which some would argue are the best neural networks. Meta AI is obviously Facebook Metaverse AI, and they have many products. I would watch them too. They have a lot of money in this area. They're investing in a lot of these products. Kind of crazy products like Reskin, which is like a set of magnets that make a kind of a skin-like product to sense touch and so on. That's actually helping in some of the communities with disabilities and so on. But there are some more ordinary products that are very interesting in the meta environment, in the metaverse and so on. For those who work in technology, just remember that AI is only as good as the data it uses. A lot of people forget that. It's very important. So a big part of any AI project is getting the data into a state where it actually is useful and is clean and so on. So before we get into how AI can use data, we need to know what big data is. So big data is defined as a project that has to handle a great amount of data in one of these three ways, either in a lot of variety of data, big variety of data, or big volume of data, or big volatility or velocity of data, or all of the above. So in variety, that can be, lots of different types of data coming from lots of different places. You can get structured data from SQL Server databases. You could get unstructured data from NoSQL databases or semi-structured data from NoSQL databases. You can get unstructured data from the Internet of Things or from, JSON devices and so on. Volume, huge quantities of data. We're now talking about petabytes even, not just terabytes. So, a lot of data is often processed in big data projects. And the speed and velocity and volatility of data can also be a huge issue for companies. And that's why it's called a big data project if it deals with any of those things. So just so that you know where the big data part fits into AI and ML, this is a typical architecture for AI and ML. So typically you're going to have data prep as your first stage, then you're going to have train and tune, and then you're going to have deploy and monitor. So data prep in any AI and ML life cycle. Data prep is all about getting the data from the actual source of the data and just collecting it and preparing it, maybe labeling it, maybe pre-processing it. So that's data prep. And that can involve a whole data pipeline. That can involve many data lakes. Typically, you're going to have at least 3 stages. You might have heard of ETL or ELT. So that's extract, transform, load, or the other way around, extract, load, and transform. So typically that's going to be as part of the data prep. So You're taking data from its source, where you might have nulls, you might have incomplete data, you might have data with no relationships to other data, that kind of thing. Might have data that just doesn't make sense, it's just not real, it's not valid, and so on. And then you're going to put it through a pipeline until that data is in good condition for use within AI and ML. So that's the first stage. The second stage is to train and tune using that data. So you typically are going to put that data in and give some rules or some decision criteria that the AI ML will use to validate that data, come up with kind of outputs, and then it will go back and say, is this output what we expected, yes or no? And if it's not what we expected, then we go back into the system and try to tune it until it gets to the point where the output is what we expect or is good enough for the next stage. So the next stage is where you do some testing of that data that's come out of that system, and you decide which of the versions of that system make most sense to put out there, and then you deploy it as a model. And those models are then monitored and checked and retrained back in to improve constantly. The whole idea is a constantly improving system. The big thing to bear in mind is on the left-hand side of that previous diagram, there's a huge big data cleanup. It's a huge amount of work, and it can involve all kinds of extracting of data from things like Internet of Things devices. So that can be a Raspberry Pi device that typically might sit out on a car or on a truck or on a train or on a wind farm, a windmill, or a solar panel, or that kind of thing. Or it might be in your phone, data coming in from your phone. It might be cameras, all kinds of devices out there, medical devices, thermometers, devices in shops, in stores, that detect different either temperatures or lighting and that kind of thing. All these things can bring data in. That data comes in typically to something like a Google Cloud object, such as a message queue like a pub sub, or an AWS object called SQS, which is a message queue, or an Azure queue, something like that, or even just a standard AMQP queue, as we used to use in the old days, like with RabbitMQ and so on. So typically that data is going to come in through some kind of message queue to buffer that data as it comes in at very high speed before it comes into the data pipeline. That might then be streamed using something like Apache Flink or Confluent Kafka or MSK Kafka. Confluent Kafka is the cloud-based version. MSK Kafka is the managed version. You can get both of those in the clouds. Something like Strim might be the streaming device, or AWS Kinesis Data Streams, or Kinesis Firehose, or Azure Event Hubs. Any of those might be used for bringing the data through into different parts of the cloud. IoT Hub and IoT Core are typically used for bringing in Internet of Things data into the cloud. Data pipelines usually involve data lakes, and data goes through various stages. So those stages could be ETL, as we talked about before, ELT, as we talked about before, or bronze, silver, gold. So that the gold data is the data that is pristine, in very good condition. Those three different data lakes would consist of the bronze data would be the data as it came in, not processed, not validated, not checked, that kind of thing. Silver would be data that has been validated and checked to a certain degree, and then gold data is the pristine data that you're actually going to load into your data warehouse typically. Other ways you can do that data pipeline include things like Azure Data Factory, AWS Glue, or it used to be AWS Data Pipeline, but that's now been discontinued. Google Data Flow. There's a few other options too, and also, Databricks has options there too. Data warehouses you might find used in the cloud are things like Azure Synapse DW, which is data warehouse sort of, AWS Redshift, Google BigQuery. There's Vertica as well. There are other options, but those are the main ones. So with ETL, which is the typical way that you transform data when it comes into the cloud, the extract part may be looking at data from SQL, from like structured database servers like SQL Server or Postgres, that kind of thing, or from NoSQL databases like Mongo or RavenDB, DynamoDB, that kind of thing. Or they might just be in files, in JSON files, in Parquet files, CSV files, XML files, or now Delta files. The data pipeline would typically remove bad data, clean up the data, move data from the old schema to a new schema, might even put ACID onto the data. So ACID is pretty much the whole idea of a data lake house, whereby you have acidic transactions. So what are acidic transactions? So atomic, complete, isolated and durable, isolated and durable is basically ACID, which is basically what relational databases have always been, but now data lakes are trying to be by putting delta on top of the data lakes. So delta on top of a data lake gives you that ACID property. So a delta lake format is really just a different type of file format. It has the Parquet data in there, but it has another layer which basically tells you which version of the data you're looking at, and which fully complete transaction that data was part of. So that allows you to do acidic transactions. And then on the right hand side you have data warehouses, and the data warehouse will typically be used for analytics of data over time, over dimensions, like geography, that kind of thing. And you're looking at metrics in that timeline over that time or over that geography and so on. So it's metrics by dimensions typically. So what part does Apache Hadoop and its components play in all of this? So for big data, Hadoop has been traditionally the way to do big data. And nowadays, a lot of the tools in the cloud especially are built on top of Hadoop and its principles. So what is Hadoop? So Hadoop is basically for big data projects. It's an open project. Apache, who are very open and push a lot of open projects through, they are the bearers of the Hadoop ecosystem pretty much. So HDFS is the file system on which Hadoop is built. So that is a highly distributed, highly performant file system. It's built for redundancy. It's built for doing tasks, multiple tasks at the same time. Parallel processing. It's built for that. Now, typically in a Hadoop environment, you also have HBase, which is a kind of database for Hadoop, if you like. And then on top of that, you have two components that can be used either or, which is MapReduce or Yarn. And we'll talk more about that later. On top of those two, just about all of the other products exist. So Hive, Pig, Mahout, Avro, Scoop, Zookeeper, Flume, Chuka, Oozie, all of these products sit on top of all of that. But nowadays, the clouds providers have built a lot of their components on top of Hadoop. So we'll talk about that in a few slides, but pretty much if you're using big data in the cloud, you're probably using Hadoop. Now, the big thing that they're all built on top of is something called Spark. So Spark sits on top of HDFS, and it supports Scala, Python, R, Java, and SQL. And there is actually a flavor of it which Azure have created, which also supports .NET and C Sharp. But basically, the pure Spark does support only Scala, Python, R, Java, and SQL. And then you have notebooks on top of Spark, which allow you to process data. And those notebooks are typically either Jupyter or Zeppelin. And you'll find that all the cloud products for big data work in cahoots with things like Jupyter and Zeppelin and Scala, Python, R, Java, and SQL, pretty much. And we'll talk about that as we go through. So in Google Cloud, you have Apache Hadoop solutions that are renamed pretty much. So for example, if you're using HBase in Hadoop, you probably want to use Dataproc in Google Cloud or Bigtable in Google Cloud. HBase and Bigtable, there's a lot of similarities between the two. In Apache Beam is very much for processing of streaming data in the Apache Hadoop system. And in Google Cloud, you would use Dataflow, which is pretty much Apache Beam for Google Cloud. Spark and Kafka, their functionality, if you like, is reproduced as Dataproc within Google Cloud. Presto can be carried out, the same things that Presto allows can be carried out by Dataproc or BigQuery in Google Cloud. And the same with Spark interactive web notebooks. Dataproc supports those. So basically everything you can use in Apache Hadoop, you can pretty much use it in Google Cloud just by knowing which product to use within Google Cloud. Most of the Google Cloud products in this area are just built directly on top of Hadoop. For ETL and ELT batch processing, Apache Airflow is being used as Dataproc or Cloud Composer. Cloud Composer has those DAGs just the same as Airflow does, and Dataproc is for data pipeline type work. So pretty much if you can find something you do in Hadoop outside of Google Cloud, you can do it in Google Cloud with one of these tools. You can actually use Hadoop, pure Hadoop, within Google Cloud as well, as you can within all the clouds. But Google has built tools on top of those to make things slightly easier for you within Google Cloud. So within Azure Cloud, you have Spark as well, but you have it within the Synapse Analytics environment. You also have some Spark tools within Azure Data Factory, but they're built into like a no-code environment. Within Synapse Analytics, you can actually get down to the code level. So you can actually do sort of, the Scala, the Python, the R, the Java, and the SQL on top. So the runtimes here show SQL runtime, an Apache Spark runtime, and a Data Explorer runtime on top of their data lake storage. But basically, this is Spark for Azure, for Microsoft Azure. In AWS, if you want to do Spark-like things, then you use EMR typically. So EMR is Elastic Map Reduce for AWS, and it's built on top of Hadoop. There are some benefits to using it. It's a little bit faster and so on, but pretty much it's just like Hadoop for AWS. And it supports things like Apache Airflow, step functions, which are very similar to some of the steps that you use in Airflow. There's Spark-like functionality, so you've got the Scala, the Python, the R, the Java, the SQL on top, and so on. And you've got that serverless option on top, which EMR provides. So you don't have to manage the servers underneath. Some of the newer data architectures you're going to see in the cloud, for example, are data lakes, which is pretty much usually read-only storage of data in a particular state. And that data may be JSON files, Parquet files. It can also be lots of other types of files as well. Data lakes are available in all three clouds. S3 in AWS provides a data lake. You can use Redshift on top of that to get to Redshift. Sorry, you can use Spectrum on top of that to get to Redshift data warehouse. Azure has ADLS2 as its data lake nowadays. It used to be blobs, but now ADLS2 is very hierarchical and is built really nicely for data lake storage. And then there's Google Cloud Storage in Google Cloud. Delta lakes are offered within the clouds too. So these are Delta files with those ACID properties that we talked about before for version history, for time travel, and so on. Delta lakes really are only useful if you're updating and deleting data, so not for read-only uses. All three clouds support some kind of data lake. Delta lake. Databricks is the Delta Lake implementation that most people prefer right now, but there are other options too. Azure is moving towards a one lake with Fabric, Azure Fabric, there we go, Azure Fabric architecture that's coming through. It's not really ready for prime time yet, but One Lake with Fabric will be the equivalent of the Delta Lakes in the future in Azure. Also, there's some Hadoop-based Delta Lake derived components as well in some of the clouds. AWS Lake Formation is a bit like data lake management plus a bit of Delta Lake, but not quite. So just be aware of that. Data lake houses. We talked about AWS with Redshift with the Spectrum layer to go down to S3 data lakes. Spectrum basically makes it's kind of like a virtualization layer, makes it look like the data lake data is in the Redshift database pretty much. As we said, Databricks implements Data Lakehouse. Azure OneLake with the shortcuts to prevent duplication produces a data lakehouse. So the OneLake idea is that you'll have many data lakes, but you can refer to an existing data lake rather than have many copies of the same data lake. Google BigQuery has connectors and data analytics options, but a lot of Google BigQuery implementations use the data lakes are stored within the actual BigQuery. You can store them on Google Cloud Storage, but they typically do ELT instead of ETL. So they load it first before they do the transformations in Google Cloud, because BigQuery is very good at managing data lakes within the actual data warehouse. Other data architectures, data mesh is the whole idea of each department owning its own data and offering that data as a service, as a contract to other parts of the organization, as a product basically, and doing all the management of that data internally to that department and just presenting the data to other departments through an API or microservice or what have you. Azure Fabric is, as I said, that new product from Azure, which is all about looking at data as a whole, using the OneLake data or Delta Lake, and having a holistic approach towards data. I think Azure Fabric is going to be the product to watch in the future, but it's definitely not there yet. It's trying to be Databricks for Azure on steroids, and I think eventually it will get there, but right now it's a new Microsoft product. and it comes with all those problems that most Microsoft products come with the first version of. So don't use it until it's a few versions down, and then I think it might be a really great product. We talked about Databricks. Databricks is actually its own company, but they provide their product on all three clouds. Databricks is really a data lake house that you can build on all three clouds. You can use a lot of Hadoop tools on top of it, and it's a great product if you don't want to use the specific cloud products.
So let's look at some typical machine learning architectures. So we talked about machine learning and artificial intelligence not happening in a vacuum. It happens as part of a huge ecosystem of data and applications and infrastructure and so on. So this diagram is an example of an infrastructure like that within AWS. This one's centered around the AWS Glue architecture, but of course there are so many different architectures that could happen. On the left-hand side here, you can see various different types of data coming in into the data collection area kind of thing, the data sources being connected to AWS Glue in this case, via crawlers and so on. The data is then cataloged, and we talked about the importance for machine learning and AI of cataloging data and putting labels on data, especially if it's like unstructured data, being able to work out what kind of data it is, that's very important. So AWS Glue has a catalog kind of built into it, so that's what's being done here. The data is then transformed, and AWS Glue has a studio in which you can transform the data. You can use notebooks and so on, like Jupyter and Neptune and so on. And then you can interactively transform your data using those notebooks, using that studio. You can transform your data without writing code or with writing code. It's up to you. There's something called AWS Glue Data Brew that allows you to transform data too. All of this operates on top of Python and Spark pretty much within the AWS environment. So there's kind of a serverless Spark version underlying all this, built onto EMR. Then you have the outputs from this really. So some of this data might be stored in a data lake so that other applications, including machine learning and AI, can take that data from the data lake and use it for to predict stuff or to analyze patterns and so on. So machine learning is one use of that data in the data lakes. The data can also go into relational databases where you might want to write queries on that data, summarize the data, that kind of thing. Big data platforms like data warehouses and so on could also use that data for analytics and reports and so on. And then there's log analytics too, and there's various other ways that you would use that data that's output. But the important thing is that data goes through a pipeline of changes, of connections, of catalogs, of transforming, so that the data is more usable at the end. So the data is purified or cleaned up, and it goes through a number of transform processes to make it more useful for things like machine learning and for analytics and reporting and so on. So here's another sample architecture, if you like. This one's for Google Cloud. So again, on the left, you have a number of different data sources coming in of different types of data. There are different options for how you process that data as it comes in on your data collection area. So PubSub is like that message queuing technology we talked about, a bit like SQS, a bit like RabbitMQ and AQMP technologies and so on. Also Azure queues. So that's one option. And then that might be followed by ETL using something like Dataflow or Data Fusion, remembering that Dataflow is very much like Apache Airflow. So they're options for infusing certain types of data like IoT data or data from databases that might come in via CDC, change data capture. Some other ways that you might ingest data. You might ingest data directly into cloud storage. Cloud storage in Google Cloud is the same as or similar to AWS S3, and also it's a bit like Azure Blobs and a little bit like Azure Data Lake S2. So it's really for blob storage or for file storage. There's also the option of bringing in Dataproc Spark processing. So if you're bringing in files in batch mode, Spark is great for batch processing of huge amounts of data coming in and so on. The cloud storage data can be loaded into BigQuery at this point, at the collection point, in which case it would be ELT because you're loading it first and then transforming it. Or it could go the other way around. It could go ETL, which basically means you transform it first and then you put it into BigQuery. In this case, the data is going into BigQuery. And as you can see, there's the three stages of data. In this case, it's bronze, silver, and gold, but that's very similar to ETL or ELT in other environments. This is basically where data is cleaned up, got rid of any bad data, got rid of any nulls, that kind of thing, and then process the data into a different format that's more useful. And then the data is there in the gold state, ready to be used by other applications. In this case, REST APIs, views, that might be materialized views and so on. The cloud storage can be used as an output from this whole BigQuery data lakes pipeline, if you like. And then that data can be used by things like Vertex AI for artificial intelligence processing. And again, refined. The data can be refined and go back and made better and so on. Data Studio is a little bit like AWS Glue Studio, and a little bit like Looker and a little bit like Power BI for reporting and analytics. And then, of course, your application systems can also take this data and use it. And then there's also the Dataproc Spark batch processing option as well. So this is a typical Google Cloud architecture for AI and ML. In Azure, typically you're going to use Synapse Analytics nowadays for machine learning. There is the option to use Azure Data Factory for some of the data ingestion and data pipeline options, but typically most people for machine learning and AI are going to use Synapse Analytics. And remember that Synapse Analytics pretty much sits on top of Hadoop, so it's very Hadoop friendly, if you like. So on the left-hand side here, again, you can see different file types coming in on the left and being ingested. Typically in Azure, you're going to store the data as it comes in into Azure Data Lake Storage. You might use Azure Queues as it comes in. You might use Event Hub, that kind of thing, IoT Hub as the data comes in. But then the data is pretty much going to go into Synapse Analytics, which is kind of a data warehouse with a lot of Hadoop-like tools like Spark. You can also use SQL. You can program in all the Spark languages, so that's Scala, Python, Java, and actually .NET, C#.NET in Azure as well. What have I missed? On R as well is another language that you can use. So basically, you're going to use Synapse Analytics to build and train in Azure Machine Learning. So you're going to use like notebooks within Synapse Analytics and that kind of thing. For machine learning, you're going to train and retrain so that the model gets better and better, that kind of thing. And there's lots of tools that you can use within Azure for AI, and we'll be talking about those in a bit. As you can see, all of this is integrated with, Azure Active Directory and Key Vault and Container Registry and Load Balancer and Virtual Network and Kubernetes and all that kind of thing, monitoring. And at the output side, typically you're going to use Power BI to analyze the data, to look at the analytics, look at the reporting, and so on. So let's go one level deeper and look at the tools and architectures used for data and for AI and ML, for artificial intelligence and machine learning. So here are typical tools that you might use in an environment like this. So for tenant segregation and integration, you'd use Azure Tenant Services. So this is kind of where you are providing a SaaS service to other customers. And for example, each of your customers might want its own data and its own application separated from all the other tenants. So for example, Microsoft has, Microsoft 365 service, and each tenant, so that might be Massachusetts government, or it might be Coca-Cola, or it might be a health company. Each tenant has its own tenant within Microsoft 365. And for example, Coca-Cola can go in and set up their own users and can turn off users that are not allowed to use it anymore, that kind of thing. And they have their own data and nobody else can see their data and so on. So that's what tenant services are for. Migration, Azure has database migration service, Azure Data Studio, and Azure Data Factory for migrating data from one environment to another. That can be from one Microsoft environment to another, but it also can be from AWS, from Google Cloud, from on-premise something else, all of those options. For data governance, Azure has Purview, which basically can just be used to make sure that your data is used in the right way. If we're talking about like health data, like HIPAA data, it's going to flag that that's different kinds of data and maybe put masking on it, or have access controls that prevent people from accessing that kind of health data in different ways, and so on. So Purview is used for that area. For data streaming, there's Azure Stream Analytics, and there's also SQL replication and CDC and a few other options as well. Data ingestion for cleanup and integration and bringing in data. One of the options there is Azure Data Factory. That's kind of like a pipeline tool. Nowadays, Synapse Analytics is getting more used for that too, so that's another option. Data warehousing, people nowadays tend to use SQL pools. I think it used to be called DW, Data Warehouse, and it's part of Synapse Analytics. So that's typically what you're going to use if you're on Azure. For data storage, for unstructured data or files, data, that kind of thing, or blobs, that kind of thing, you're going to use either ADLS2, which is the data lake option, or the blob storage, or the file storage. So the data lake option it has that hierarchy built in, which makes it that little bit easier to process data that's typically held in a data lake. So that's why people like to use ADLS2 better. But if you're just storing, blob storage is cheaper, so just use blob storage. File storage is a bit more like NFS, kind of file sharing kind of thing. Business intelligence, so this is like analytics and reporting. Power BI is the main tool in Azure. If you're trying to make sure that your data is ACID, as in atomic and consistent and isolated and durable, even though you're using it for big data, then there's two ways to do that, using Parquet files and using Databricks within Azure. So Databricks is kind of the way most people do that right now, but Azure really wants you to start using the Azure tools, and in the future that's going to be something called Fabric and OneLake. But right now, for ACID data tools and data manipulation, Databricks is probably a little bit more there than the other Azure options right now. For data engineering, Synapse is a good tool to use for that. It has the whole Spark thing going on and the whole SQL thing going on. You can have notebooks and so on. It's pretty much a Hadoop-based tool set. So it's pretty good for analyzing and massaging data and manipulating data and so on. And again, that's the reason it's good for data science. So it's pretty much Spark for Azure with a few extra bells and whistles. So data science, Synapse is pretty good for that, and real-time analytics. So, if you need to, as the data comes in, you need to create more data from it in real time, then Synapse is probably a good option for that. There are some no-code insights and actions from Data Activator. And then there's Data Lakehouse options. So Data Lakehouse is that acid of the data in the big data world. So Databricks with Delta Lake, as I said, is what I would recommend. I know Azure would prefer you to use Fabric with OneLake, but right now it's really not there yet. I think the Delta Files and the Delta Lake are kind of there, but some of the Fabric and some of the OneLake areas are still to be cleaned up or made good right now at this moment in time. So as I said here, the future state is for Azure is OneLake and Fabric, not quite there yet. The idea behind them is to have a unified view of the data, a unified environment in which to do all your data work. That's pretty much what Databricks is already. Databricks runs on all three clouds and a few other places too. So Databricks right now, I think, is that unified environment, but I think Azure are trying to make Fabric and OneLake that future state. So keep that in mind. So AWS has a wealth of tools in the data area. As you can see here, EMR is that almost like a Spark-based data file system for AWS, which it's very similar to Hadoop or HDFS. So it's called EMRFS when you're using it as HDFS kind of mode. There's also interactive query tools like Amazon Athena. There's analytics tools like Open Search Service. For real-time analytics as the data's streaming in kind of thing, Kinesis Data Streams is a great one. Kinesis Data Firehose is very similar to Kinesis Data Streams in some ways, but typically it's a little bit slower and you might want to do some processing before bringing that data in. Kinesis Data Analytics works with Firehose or data streams to bring in data in and analyze it as it comes in kind of thing. There's managed streaming for Kafka, which is MSK. That's pretty much Kafka for AWS. There's also Confluent Kafka, which you can use in AWS, but that's like a cloud-based Kafka, so it's not just managed, it's completely serverless. So that's an option. For your data warehouse in AWS, typically you're going to use Redshift. There are other options. For example, Vertica, which is a massively parallel processing database from what used to be Micro Focus and is now OpenText. But Redshift is pretty much the one you're going to use. Redshift also has Spectrum, which basically makes the whole thing into like a data lakehouse environment, so that Redshift itself can go to the data lake in S3 and get data as though it's in a table in Redshift. It's kind of virtualization. So that's another option. Amazon QuickSight is great for visualizing data in AWS. Data integration, we talked about AWS Glue, so it's pretty much like a data pipeline tool, a bit like Apache Airflow, but kind of got graphical DAGs and so on, so that you don't have to do any programming for some of that and so on. There's lots of relational database options. Aurora comes in a number of flavors. I think it's MySQL and PostgreSQL. Relational database comes in SQL Server, MySQL, Postgres, Oracle, MariaDB. I think that's all of them. There's a key value database, which is DynamoDB. So that's a NoSQL database. DocumentDB, which is another NoSQL database, which is for documents, document database. Elasticache is more of a caching, so like a memory caching database. It's a bit like Redis and so on. Amazon TimeStream is for time series data. Ledger database is for like accounting data pretty much. Keyspaces is a wide column database. So that's a little bit like Bigtable in Google Cloud. You know, a lot of data goes into a single column kind of thing. So that's pretty much Keyspaces. And then MemoryDB is another kind of NoSQL database, but it's a little bit more in memory, so it's a little bit faster and so on for certain types of applications. Another example architecture for AWS is the EMR database, or not database, sorry, data platform. EMRFS is very much like HDFS, like Hadoop file system. It's just a little bit better it's a bit faster and it's better integrated with AWS tools and so on like that. So on the left hand side, EMR Studio or SageMaker Studio may be bringing in data, and then you might have a data pipeline orchestrated in Apache Airflow or in Amazon managed workflows for Apache Airflow, which is called MWAA. Or you might have AWS step functions creating the workflow or the data pipeline. Then the data ends up in EMR itself, and as I said, that's pretty much HDFS. On top of that, you've got Spark and Hadoop tools and so on. So you can use, you know, any of the Spark tools, so Scala, Python, R, Java, and so on. And then on top of that, Hive and Pig and notebooks and things like that. So then these run on top of EC2 instances. Typically, EMR typically runs on top of EC2 instances. There is a serverless option for EMR, which means you don't have to manage the EC2 instances underneath. You don't have to manage the nodes and so on. And there's also an EKS option, which is Kubernetes. So there's a lot of options there. If you use EC2, you've got the option of using, you know, reserved EC2s or spot EC2s to reduce the cost and so on. And the output from all of this, often the data will go into S3, into a data lake for processing for different workloads. So, you know, this is just an example of a data architecture within AWS. This is just another example of an architecture within AWS. In this case, it's streaming in data, big data, from social media of different types. So in this case, it's ingesting from Reddit, from YouTube, from RSS news feeds, from Twitter. You know, it could be Facebook. You know, it could be everything. So that data is coming in, and you've basically got you know, a Lambda function processing some of that data as it comes in. Event bridge connecting one Lambda function to another or other parts of the architecture to it. S3 bucket containing JSON maybe from those social media outputs and so on. DynamoDB, you know, having those key value pairs or little bits of information, little bits of JSON that come in from those social media on the left-hand side. And then you have Kinesis data stream kind of taking that data in a very speedy way straight into a Lambda function, which then sets off a step functions workflow, which can be, you know, the AI part of that can be used is like recognition, which, you know, does facial recognition of photos, that kind of thing. Comprehend, which understands words and text and so on, and makes decisions based on that. Amazon Translate, which can translate from one language to another, and so on. So there's a lot of things that can be done in that step functions workflow there. And as you go along, the data can be stored in S3 buckets, so you might have many data lakes in a data pipeline like this. Again, EventBridge might connect that to another Lambda function. Kinesis Data Firehost might take that data and do some processing before it goes into another S3 bucket, another part of the data pipeline. AWS Glue might be used to transform some of that data, do an ETL, that kind of thing. And then QuickSight might be used to analyze, the outputs of some of this data. So, these are all example architectures that you might use machine learning components within. Here's another example of how big data and machine learning can be part of a whole architecture. Your devices on the left-hand side, remember that could be any Internet of Things device. So that can be your cell phone or a sensor on a wind farm or on a thermometer and so on. That data comes in here via Kinesis data streams, which is a very fast way of getting data into the system. Some of it will go off to Kinesis Data Firehost, and some of it will go off to Kinesis Data Analytics for Apache Flink. That data might transform that data before putting it through Amazon TimeStream, making it available in different time slots so that you know which time slot that data came in. Grafana might use that for logs. Analytics might use that to make trends or graphs based upon that data. And then machine learning might use that data to make predictions for the future, or to analyze patterns in the past, or to learn from the data, depending on whether you're going to use models, LLMs, and so on. On the Kinesis Data Firehose tree, you've got batch records coming in to an AWS Lambda, and then that data being put into a data lake, kind of refined data being put into a data lake, and also being used as part of this machine learning. So this is just examples of how the components of AWS can fit together from a data perspective and from a machine learning perspective. Here's an example architecture for AI and ML in Azure. So on the left-hand side, you've got, on the bottom, I should say, you've got storage of data going through the three different stages: the bronze, the silver, and the gold. So bronze is when data comes in, it's not in very good formats, it needs cleaning up and so on. The silver is once it's processed a little bit and it makes a bit more sense. And then gold is when it's completely pure and usable data, very good quality data. So those bronze, silver, and gold will be stored in Azure Data Lake storage typically. So that's 3 different data lakes. The Delta Lake might be the gold version. Delta Lake allows for ACID, so you can actually update the data. Typically right now that would be in Databricks, Delta Lake, but you can use Delta files on Azure Data Lake storage. But really Databricks has everything around Delta Lake built in. So at the top you'll see, Azure Databricks is kind of manipulating that flow between the 3 data lakes before putting that data in through the machine learning web services. And then Azure Kubernetes might be processing that data from the machine learning web services. Here's an example modern data architecture in Azure. On the left, you can see files coming in different formats, in streams or in batch files and what have you. Any data that's on the whitelist comes in and gets put into the data lake in the transient zone, which means it's not quite ready for processing. It needs something done to it. Other data might come straight into Data Factory, which basically is like a data pipeline of transforming data from one format to another, pretty much in many cases. The Data Factory also brings in some data from on-premise data sources in this diagram. So that data all comes in. There's like an Azure function that comes in and does some processing of some of that data before it goes through to the data lake, data pipeline, if you like. So there's 3 data lakes. There's a raw zone data lake, there's a process data lake, and there's an analytics data lake. All stored on ADLS, which is Azure Data Lake Storage Gen 2. Databricks in this case is managing that data pipeline from those 3 different data lakes. And then the data eventually ends up in SQL pools, which it used to be data warehouse, for access by other applications and machine learning, things like Cosmos DB APIs, Power BI, and so on. You can see along the top there the tenant services we talked about already, Key Vault, which is used for security to make sure that only we have access to our data, that kind of thing. Log Analytics to look at the logs and make decisions based upon those. Purview, we talked about basically the data quality and governance side of things. And then management connectivity to connect between different parts of Azure and on-premise and things like that. Azure DevOps is all about things like Terraform and so on, using those to generate infrastructure in an automated fashion, or doing CI/CD pipelines, that kind of thing, automating application development and so on. Here's an example of how you might do Hadoop on Azure. So again, you've got data coming in on the left from all different kind of sources. Apache Hadoop runs on HD Insight in Azure, and you can do ETL using HD Insight. Apache Spark would be on HD Insight and would be doing that kind of processing, the batch processing of data from one stage to another, one data lake to another, part of the data pipeline pretty much. That data could be stored in Azure Storage or Azure Data Lake Store. Remember, Azure Data Lake Store is really the data lake in the hierarchical manner. Azure Storage is just literally storage of files, pretty much. On top of Spark, you also have Hive and other tools that you would typically have on Spark, like Pig and so on. So you can have interactive queries on HD Insight. And then there's BI models and so on using Xscale. Again, all these Hadoop tools, often sit in the cloud on top of the cloud's tools themselves. So this is the future state of data in Azure, the way that Microsoft sees it. So it's very holistic, a very holistic view of the data. It's very similar to the Databricks view of what is there now for Databricks. So one lake is like having one big data lake where all the data is viewed through the same pane of glass, if you like, single pane of glass. Data would be held in data lake houses, in Delta format, in Parquet format, Delta Lake, Parquet format, same thing. And you could analyze those using all the tools at the top, kind of thing. So you'd have one layer of security that is across all of the data, and that would be access controls and so on. But then the top layers will be how you would manipulate that data, how you would access that data. So a lot of these tools are already existing in Azure. It's just that with Fabric in the future state, these are all going to be much more united and holistic, if you like, one view of the data through all of the different tools. So Synapse Data Warehousing already exists, but in Fabric, data warehousing is going to be much more holistic. Synapse Data Engineering, again, you're going to be able to manipulate data across multiple data lakes and things like that much more easily. Data Factory, the pipelines and so on are going to be much more integrated, the whole view of the data with all the other tools and Synapse tools and Power BI tool. And again, in AWS, the equivalent of Hadoop tools is EMR. Remember that EMR-FS is very much like HDFS, Hadoop file system, for processing big data. So all the tools around EMR are very much like Hadoop tools, and in some cases are Hadoop tools. So there's connectors with all the AWS tools as well, which makes it just that little bit easier to use within AWS. And you've got all the things like Kafka will sit on top of it, but also Kinesis will sit on top of it. So you've got the AWS tools as well as the Apache tools. So that's pretty much how you would use EMR within the AWS ecosystem. These are just some resources that I think might be useful for you to find out more, either about AI or about data or about the cloud in general, and so on. So this is just a little bit about how you provide data to generative AI applications. So we talked about those models, the LLMs and so on, and how you can refine them by using RAG. So RAG is basically relevant data being kind of fed back into these foundational models to make them more accurate and so on. And you can use that to fine-tune a foundational model based on your curated labeled data. So your data that comes in gets labeled and curated the more it goes through, and it gets more accurate and so on. And then you can train your own purpose-built LLM. Kind of, you have the basic LLM that you get from ChatGPT or what have you. It's actually called GPT. And then you put your own data on top of it to make it better, kind of thing. So they're just different ways of getting data into generative AI applications. And this is just trying to explain that generative AI applications, they take user inputs and they take a prompt that's generated from the application, and that's what creates the LLM, the large language model. So part of the generative AI application itself is instructions for the model, so from templates and so on of how to do something. So for example, if a model was going to create a Python application, there might be a template for how all Python applications should look. They have, a basic format, and then there's kind of like parameters that need to be passed in, and some of those are actual whole templates for other parts of the application. And then situational context, that might be, the context in which someone's asking for this piece of code. So are they asking for it in a health context or a financial services context, and so on. And then the semantic context is, what do they mean by what they're asking for? So that's all about analyzing the sentence that you type in as a prompt to the generative AI application and trying to work out what you mean by it. And everyone that's ever worked in search engines knows that part is very difficult. Working out what the person actually means by what they've typed in, as opposed to what they think they mean or what you think they mean, that can be very tricky. So what are the semantics? What do they mean by, they might have typed it in wrongly, they might have made a spelling mistake, a grammatical mistake, and so on. And the generative AI application has to kind of work out what they really meant to ask for and what context they're in might help them to know that, and that helps to refine the model and make it better. Now, in some cases, the semantic context might actually be put into the LLM. So this is where, the semantics are kind of refined and made better as you go along. So you learn better what someone meant by what they typed in because you've seen it before, and this is the decision you made based on it and how well it was weighted. So was it a good output or a bad output? Usually when you use ChatGPT, it asks you afterwards, was this really what you wanted, or would you rate this to tell me 1 to 5 whether this was good or bad as a response? And that can feed back into the model and tell it how good those semantics were interpreted. So that becomes part of the model itself. And this is where you fine-tune your model by feeding the responses back and back out. So you keep learning from what you sent back as a response, and when they rate the response, you find out how good it was, and then you feed that back into the whole model. If you want to start working with Azure on data and AI, here are some links that help you do that. And they'll help you build a web app with different languages, provision a machine like a virtual machine, create a database, create a serverless function, and so on.